There comes a quiet moment in life, often after 60, when the body begins to whisper truths we once ignored. Muscles that once responded instantly now hesitate. Strength fades not dramatically, but subtly, as if the body is asking a question rather than making a statement. And in that question lies urgency, because muscle loss is not merely about appearance or power, it is about independence, resilience, and dignity. The remarkable truth is that this process is not fixed. Biology is not passive. Even after 60, the body is still listening, still adapting, still waiting for the right signals. Muscle loss after 60 is often described as a simple shortage, as if the body suddenly forgets how to use protein or mysteriously stops responding to effort. But when we look closely at human biology, a more subtle and more hopeful truth emerges. The aging body is not broken, it is miscommunicating. Signals that once traveled cleanly between nutrients, hormones, nerves, and muscle fibers begin to blur. The message is no longer received with the same clarity, not because the message is absent, but because the system has become resistant, distracted, inflamed, and metabolically strained. Sarcopenia, in this light, is not an irreversible decline but a conversation that has lost its rhythm. In younger years, muscle tissue responds quickly to stimulation. A meal rich in amino acids sends a clear signal to muscle cells to repair and grow. Physical movement activates mechanical sensors that trigger protein synthesis. Hormones such as insulin and growth factors act as reliable messengers, opening cellular doors so nutrients can enter and be used effectively. With age, these systems do not disappear, but they lose sensitivity. Insulin still circulates, but muscle cells do not listen as attentively. Amino acids are present, but the signal they carry is weakened. The result looks like deficiency, even when intake is adequate. One of the most important shifts that occurs with aging is anabolic resistance. This is the reduced ability of muscle to respond to the same protein stimulus that once worked effortlessly. A younger muscle might respond robustly to a modest amount of protein, while an older muscle requires a stronger, more sustained signal. This does not mean more protein alone is the answer. If the cellular environment is inflamed, insulin-resistant, or energetically compromised, simply increasing protein is like speaking louder in a room full of noise. The issue is not volume, but clarity. Inflammation plays a central role in this communication breakdown. Low-grade chronic inflammation increases steadily with age, often unnoticed. It interferes with signaling pathways inside muscle cells, particularly those involved in protein synthesis. When inflammatory molecules circulate persistently, muscle cells prioritize defense over growth. They become cautious, conserving resources rather than building tissue. In this state, even high-quality protein can fail to trigger muscle repair because the cell does not feel metabolically safe enough to invest in growth. Another layer of this problem lies in insulin signaling. Insulin is not merely a blood sugar hormone, it is a powerful anabolic signal for muscle. It helps shuttle amino acids into muscle cells and activates pathways that stimulate protein synthesis. As insulin sensitivity declines with age, muscles receive fewer of these signals, even when insulin levels are high. This creates a paradox where the body appears to have enough nutrients, yet muscle tissue behaves as if it is deprived. Again, this looks like a deficiency, but it is fundamentally a resistance problem. Mitochondrial health further complicates the picture. Muscle cells are energetically demanding, and mitochondria are the engines that power repair and contraction. With age, mitochondrial efficiency declines due to oxidative stress, nutrient imbalances, and reduced physical activity. When energy production falters, muscle cells become less responsive to anabolic signals. Growth is an energy-intensive process, and cells with limited energy availability will naturally downregulate it. In this context, muscle loss becomes an adaptive response to perceived scarcity, not a failure of will or nutrition. The nervous system also participates in this communication loop. Motor neurons that activate muscle fibers can lose efficiency over time. When neural signals weaken, muscles receive less frequent and less precise instructions to contract. Disuse accelerates breakdown, and breakdown further reduces responsiveness. This creates a feedback loop where inactivity reinforces resistance, and resistance discourages movement. Yet even here, the system remains plastic, capable of adaptation when signals are restored gradually and consistently. Digestive changes add another subtle layer. As people age, digestion and absorption of nutrients can become less efficient due to changes in stomach acid, enzyme production, and gut microbiota. This does not mean protein is absent, but that its delivery becomes uneven. Amino acids may enter the bloodstream more slowly or inconsistently, weakening the anabolic signal to muscle. When digestion is compromised, the message arrives fragmented, and muscle cells respond accordingly. What is striking is that none of these processes represent a permanent shutdown. They are adaptive responses to an internal environment that has shifted toward stress, inflammation, and metabolic instability. When that environment improves, communication improves. When inflammation is lowered, insulin sensitivity restored, mitochondrial function supported, and digestion stabilized, muscle cells begin to listen again. The same biological machinery that built muscle earlier in life is still present, waiting for conditions that justify its activation. This perspective changes the emotional narrative around aging. Instead of viewing muscle loss as punishment for time passing, it becomes feedback from a system asking for support rather than force. Aggressive strategies that focus solely on protein loading or extreme exercise often fail because they ignore the underlying communication barriers. In contrast, approaches that reduce metabolic noise allow even moderate signals to be effective again. Understanding muscle loss as a communication problem also restores agency. It suggests that small, consistent changes can have outsized effects because they improve signal clarity rather than brute input. Improving sleep enhances hormonal signaling. Reducing inflammatory foods lowers background interference. Supporting gut health improves nutrient delivery. Gentle resistance training reawakens neural pathways. Together, these interventions re-establish dialogue between the body's systems. Perhaps most importantly, this framing respects the intelligence of the aging body. The body is not malfunctioning, it is adapting to what it perceives as a hostile environment. When nutrients spike unpredictably, when inflammation is constant, when energy is unstable, the body chooses preservation over growth. When the environment becomes stable again, the body responds with renewed adaptability. Muscle tissue, even in later decades, retains a remarkable capacity for regeneration when signals are coherent. Studies consistently show that older adults can increase muscle mass and strength when metabolic conditions are optimized. This would not be possible if the problem were simple depletion. It is possible precisely because the system is intact, merely undercommunicated. Seeing sarcopenia through this lens invites patience rather than urgency, curiosity rather than fear. It shifts the focus from chasing numbers to restoring relationships within the body. Protein becomes a message rather than a substance, movement becomes conversation rather than exertion, and recovery becomes as important as effort. When communication improves, muscle follows, quietly and steadily, responding not to force but to understanding. For much of modern nutritional history, protein has been treated as an isolated entity, measured, counted, and elevated above nearly every other dietary component when muscle health is discussed. Yet the human body does not experience protein in isolation. It experiences food as a complex biological message, one that arrives bundled with fiber, minerals, phytochemicals, and metabolic signals that shape how protein is used. Lentils represent this complexity in a way that is particularly relevant for aging physiology, because they deliver protein not as a blunt instrument, but as part of a coordinated system that supports the entire environment in which muscle tissue exists. At a fundamental level, lentils are rich in plant-based protein, providing a substantial amount per serving without the metabolic burden often associated with concentrated animal proteins. But their true value emerges when we look beyond grams and into context. Each lentil contains a matrix of soluble and insoluble fibers that slow digestion and modulate nutrient absorption. This controlled release creates a steady availability of amino acids in the bloodstream, offering muscle cells a prolonged opportunity to synthesize protein rather than a brief surge followed by scarcity. For aging muscles that require sustained signaling to overcome anabolic resistance, this pattern is especially valuable. Fiber, often dismissed as irrelevant to muscle, plays a central role in this process. As fiber travels through the digestive tract, It feeds beneficial gut bacteria, which ferment it into short-chain fatty acids. These compounds have systemic effects, reducing inflammation and improving insulin sensitivity. Lower inflammation removes one of the primary barriers to muscle protein synthesis, while improved insulin sensitivity enhances the delivery of amino acids into muscle cells. In this way, the fiber in lentils indirectly amplifies the effectiveness of the protein they contain. Minerals present in lentils further support muscular function in ways that isolated protein cannot. Magnesium is essential for muscle contraction, energy production, and enzymatic reactions involved in protein synthesis. Potassium helps regulate nerve impulses and fluid balance, both critical for maintaining muscle strength and preventing fatigue. Iron supports oxygen delivery to muscle tissue, ensuring that mitochondria receive the oxygen they need to produce energy efficiently. Zinc contributes to tissue repair and immune balance, helping muscle cells recover without excessive inflammatory response. When these minerals are delivered together with protein, they create a biochemical environment conducive to regeneration rather than stress. Antioxidants and polyphenols found in lentils add another protective layer. Aging muscle is vulnerable to oxidative damage, which disrupts cellular membranes, impairs mitochondrial function, and interferes with anabolic signaling pathways. The plant compounds in lentils neutralize reactive oxygen species, reducing oxidative stress at the cellular level. This protection preserves the integrity of muscle cells, allowing them to respond more effectively to growth signals. Protein consumed in an oxidative environment is often diverted toward repair of damage rather than building new tissue, so reducing oxidative burden increases the efficiency of protein utilization. There is also a hormonal dimension to consider. Lentils have a low glycemic impact, meaning they do not cause sharp spikes in blood sugar. Stable glucose levels lead to more stable insulin responses, avoiding the repeated surges that contribute to insulin resistance over time. Since insulin is a key anabolic hormone for muscle, maintaining its sensitivity is crucial. By promoting glycemic stability, lentils help preserve insulin's role as a messenger that opens the door for amino acids to enter muscle cells. Digestive tolerance is another often overlooked factor in aging nutrition. Heavy animal proteins can be difficult to digest for older adults due to reduced stomach acid and enzyme production. This can lead to incomplete digestion, bloating, and inefficient amino acid absorption. Lentils, when properly prepared, are generally easier to digest and place less strain on the digestive system. Improved digestion means more consistent nutrient absorption, which translates into clearer metabolic signaling and better muscle support. The synergy within lentils also extends to satiety and appetite regulation. Adequate protein intake requires consistent eating patterns, yet appetite often declines with age. The combination of protein and fiber in lentils promotes fullness without heaviness, encouraging regular meals rather than sporadic intake. Regular nutrient exposure reinforces metabolic rhythms, which in turn supports muscle maintenance. Muscles thrive on consistency, responding best when nutrients arrive predictably rather than erratically. From a cellular perspective, lentils provide not only building blocks but also regulatory signals. Amino acids such as leucine activate pathways involved in muscle protein synthesis, while the surrounding nutritional context determines whether those pathways remain active. Inflammatory diets can blunt these signals, while anti-inflammatory, fiber-rich foods enhance them. Lentils consistently deliver protein within a regulatory framework that favors anabolic activity rather than resistance. There is also a broader physiological harmony at play. Muscle health is inseparable from cardiovascular health, metabolic health, and gut health. Lentils support all three simultaneously. Improved circulation delivers nutrients more efficiently to muscle tissue. Better metabolic control reduces the catabolic effects of chronic stress hormones. A healthier gut improves immune balance, reducing the low-grade inflammation that accelerates muscle breakdown. Each of these systems reinforces the others, creating a network effect where the impact of lentil-based nutrition exceeds the sum of its parts. This integrated support is particularly important in later life, when the margin for error narrows. The body becomes less tolerant of extremes and more responsive to balance. Foods that deliver single nutrients without context may meet numerical targets but fail to produce functional outcomes. Lentils, by contrast, align with the body's preference for coordinated input, providing protein in a form that respects the interconnectedness of biological systems. Perhaps most importantly, lentils invite a shift in mindset. They challenge the idea that strength must come from intensity, excess, or dominance over the body. Instead, they represent nourishment as cooperation. They work quietly, steadily, supporting muscle not through force but through restoration of balance. In doing so, they remind us that muscle health is not just about what we add, but about the environment we create for the body to use what it receives. As the human body ages, one of the most profound yet least visible changes occurs not in muscle itself, but in the way muscles respond to the signals meant to nourish and rebuild them. Insulin sensitivity sits at the center of this process, quietly determining whether nutrients become strength or are diverted elsewhere. Insulin is often misunderstood as merely a regulator of blood sugar, but biologically it is a messenger of abundance, a signal that tells cells resources are available and growth is permissible. When muscle cells remain sensitive to insulin, they open their doors readily, allowing glucose and amino acids to enter and fuel repair. When that sensitivity declines, the message grows faint, and muscles behave as though they are underfed even when nutrition is adequate. With age, insulin resistance develops gradually, influenced by physical inactivity, chronic inflammation, poor sleep, and repeated blood sugar spikes. Muscle tissue becomes less responsive, requiring higher levels of insulin to achieve the same effect. This state is metabolically noisy. Elevated insulin circulates in the bloodstream, yet muscle cells fail to fully respond. Amino acids linger outside the cell, unused or redirected, while protein synthesis pathways remain underactivated. The result is a slow erosion of muscle mass that appears inevitable but is in fact conditional. The restoration of insulin sensitivity changes this dynamic fundamentally. When muscle cells once again respond to insulin signal, nutrient flow improves dramatically. Glucose enters muscle cells efficiently, replenishing glycogen stores and providing energy for contraction and repair. Amino acids follow, activating intracellular pathways that stimulate protein synthesis. This re-established flow transforms the metabolic environment from one of scarcity to one of sufficiency. Muscles no longer perceive a threat and can invest in maintenance and growth. Inflammation is one of the strongest disruptors of insulin signaling. Pro-inflammatory molecules interfere with insulin receptors on muscle cells, distorting the signal before it can be transmitted internally. Chronic low-grade inflammation, common in older adults, effectively acts as static on the line. Reducing inflammation clears this interference, allowing insulin's message to be received with greater clarity. When inflammation subsides, the same amount of insulin produces a stronger anabolic response, improving muscle preservation without increasing hormonal demand. Mitochondrial health is closely tied to insulin sensitivity. Mitochondria regulate how glucose is used once it enters the cell. When mitochondrial function declines, glucose metabolism becomes inefficient, leading to accumulation of metabolic byproducts that further impair insulin signaling. Improving insulin sensitivity enhances glucose utilization, which in turn supports mitochondrial efficiency. This reciprocal relationship creates a positive feedback loop where energy production improves, oxidative stress decreases, and muscle cells regain metabolic flexibility. Physical movement plays a crucial role in restoring insulin sensitivity, especially resistance-based activity. Muscle contractions stimulate glucose uptake independently of insulin, temporarily bypassing resistance. Over time, this repeated stimulation increases insulin receptor density and improves intracellular signaling pathways. The muscle becomes more responsive not only during activity but at rest as well. Nutrients consumed after movement are more likely to be directed into muscle tissue, amplifying the anabolic effect of protein intake. Dietary composition strongly influences insulin sensitivity as well. Frequent consumption of refined carbohydrates and ultra-processed foods overwhelms glucose regulation, forcing repeated insulin surges that desensitize receptors. In contrast, foods that release glucose slowly stabilize insulin signaling. When blood sugar remains steady, insulin is released in moderate, controlled amounts, preserving receptor responsiveness. This steadiness is essential for aging muscles, which depend on consistent rather than extreme signaling to maintain mass. Improved insulin sensitivity also reduces muscle breakdown. In insulin-resistant states, the body compensates by increasing stress hormones that promote gluconeogenesis, often at the expense of muscle protein. Muscle tissue becomes a resource to be broken down rather than preserved. When insulin sensitivity improves, this catabolic pressure eases. The body no longer needs to sacrifice muscle to maintain blood sugar, allowing protein turnover to shift toward rebuilding rather than loss. There is a neurological dimension to this process as well. Insulin signaling in the brain influences appetite, satiety, and motivation for movement. Insulin resistance can blunt these signals, reducing physical activity and reinforcing sedentary behavior. As sensitivity improves, neural signaling becomes clearer, supporting more natural movement patterns and reinforcing the cycle of muscle use and maintenance. This highlights how insulin sensitivity extends beyond muscle cells into whole body regulation. Sleep quality also intersects with insulin sensitivity. Poor sleep disrupts hormonal balance, increasing insulin resistance and inflammation. When sleep improves, insulin signaling becomes more efficient, even without changes in diet or exercise. This demonstrates how muscle health depends on systemic harmony rather than isolated interventions. Each improvement in lifestyle reinforces insulin sensitivity, which then magnifies the impact of nutritional and physical inputs. From a cellular signaling perspective, insulin activates pathways that work in concert with amino acid sensors. When insulin sensitivity is high, these pathways converge, amplifying the signal for protein synthesis. When sensitivity is low, the pathways remain fragmented, and the anabolic response is blunted. Restoring insulin sensitivity reunifies these signals, allowing muscle cells to interpret nutrients as a clear directive to rebuild. Perhaps the most encouraging aspect of this process is its reversibility. Insulin resistance is not a fixed feature of aging but a modifiable state. Studies consistently show that older adults can improve insulin sensitivity through modest changes in diet, movement, sleep, and stress management. As sensitivity improves, muscle tissue responds accordingly, regaining responsiveness that was assumed to be lost. This reframing alters the narrative of muscle loss. Instead of viewing aging muscles as unresponsive or exhausted, they can be seen as cautious, waiting for reliable signals before committing resources. When insulin sensitivity is restored, those signals become trustworthy again. The body responds not with dramatic transformation but with steady resilience, preserving strength through improved communication between nutrients, hormones, and cells. As the body ages, it begins to favor rhythms over extremes, continuity over bursts, and steadiness over shock. This shift is not a weakness but an adaptation, reflecting changes in digestion, hormonal signaling, and cellular responsiveness. In this context, the way protein enters the system becomes just as important as how much is consumed. Plant protein, particularly when delivered through whole foods, aligns naturally with the aging body's preference for sustained nourishment rather than rapid stimulation. Its slower digestion profile creates a prolonged presence of amino acids in the bloodstream, offering muscle tissue a continuous signal for repair rather than a fleeting command. In younger individuals, rapid spikes in amino acids can effectively trigger muscle protein synthesis. The cellular machinery responds quickly, initiating growth pathways with minimal resistance. With age, however, anabolic resistance blunts this response. Short-lived surges in amino acids may fail to overcome the threshold needed to activate protein synthesis meaningfully. Plant proteins, by digesting more gradually, maintain amino acid availability over several hours, increasing the likelihood that muscle cells receive sufficient exposure to initiate and sustain repair processes. This extended amino acid curve has important metabolic implications. When amino acids are available steadily, the body is less likely to oxidize them for immediate energy. Instead, they are preserved for structural functions such as tissue repair. Rapid protein digestion, by contrast, can flood the bloodstream briefly, exceeding immediate needs and leading to amino acid oxidation. For aging muscles that require efficient use of available nutrients, this difference matters significantly. The digestive system itself benefits from this slower process. Plant proteins are naturally embedded within a fibrous matrix that moderates enzymatic breakdown. This reduces digestive strain and supports more complete absorption. In older adults, where digestive efficiency may be reduced, gentler digestion improves nutrient delivery and reduces gastrointestinal discomfort. Better digestion enhances consistency of intake, which is crucial for maintaining muscle over time. Hormonal responses also differ based on digestion speed. Rapid protein digestion often triggers sharp insulin responses, which can be problematic in individuals with reduced insulin sensitivity. Slower digestion produces a more balanced hormonal profile, supporting insulin's anabolic role without overwhelming receptors. This steadiness helps preserve insulin sensitivity, allowing muscles to remain responsive to anabolic signals over the long term. There is also an interaction with circadian biology. Muscle repair is not a constant process but follows daily rhythms influenced by feeding patterns, activity, and sleep. Sustained amino acid availability supports these rhythms, providing muscle cells with resources during extended recovery periods, including overnight repair. This is particularly relevant for older adults, whose recovery windows may be longer and more sensitive to disruption. From a cellular signaling standpoint, prolonged amino acid exposure supports sustained activation of protein synthesis pathways. Rather than a brief activation followed by rapid decline, these pathways remain engaged long enough to produce meaningful structural changes. This continuous signaling aligns with the slower but persistent adaptive capacity of aging muscle tissue. Plant protein sources also tend to be lower in compounds that promote oxidative stress when consumed in excess. This reduces the metabolic cost of digestion and assimilation. Lower oxidative stress preserves mitochondrial function, ensuring that muscle cells have the energy needed to convert amino acids into functional tissue. When energy availability is stable, the efficiency of protein utilization improves. Another important consideration is nitrogen balance. Maintaining muscle mass requires a positive or neutral nitrogen balance over time. Sustained amino acid delivery supports this balance more reliably than intermittent spikes. Plant proteins' gradual digestion helps maintain nitrogen availability across longer periods, reducing the risk of net muscle protein loss between meals. There is a psychological dimension as well. Plant-based protein sources are often consumed as part of meals rather than as isolated supplements. This encourages regular eating patterns, which reinforce metabolic stability. Regular nutrient intake reduces stress responses that can promote muscle breakdown. Muscles are more likely to be preserved in an environment where the body perceives predictability and adequacy. The slower nature of plant protein digestion also interacts favorably with physical activity. When amino acids remain available for extended periods, even low-intensity or delayed movement can contribute to muscle repair. This is particularly valuable for older adults who may not engage in intense exercise but still benefit from consistent movement throughout the day. Importantly, this does not suggest that plant protein is weaker or inferior. It suggests that its timing and delivery are better matched to the physiology of aging. Muscle adaptation in later life is less about maximal stimulation and more about sustained support. Plant protein provides this support in a way that respects the body's changing priorities. When viewed through this lens, muscle preservation becomes a process of alignment rather than opposition. The body is not resisting strength, it is requesting conditions under which strength can be maintained safely. Slower digestion, steady amino acid availability, balanced hormonal responses, and reduced metabolic stress create those conditions. Plant protein fits into this framework naturally, offering nourishment that works with aging physiology rather than against it. Over time, this sustained approach accumulates effects that may not be dramatic day to day but are profound over months and years. Muscle tissue responds quietly, maintaining mass and function through continuous repair rather than sporadic rebuilding. This gradual resilience reflects the deeper wisdom of the aging body, which favors endurance over intensity, continuity over excess, and balance over force. There is a deeply ingrained belief in modern health culture that strength must be demanded from the body, that progress comes only through pressure, intensity, and discipline imposed from the outside. This belief is especially strong when aging enters the picture, as if time itself must be challenged aggressively to prevent decline. Yet biology does not operate on ideology. The human body responds not to force, but to conditions. Strength does not emerge because the body is pushed harder. It emerges when the internal environment becomes supportive enough for adaptation to occur. This distinction becomes increasingly important with age, when tissues grow more cautious and systems prioritize survival over performance. Muscle tissue is not inert matter waiting to be sculpted. It is living, sensing, adaptive tissue that constantly evaluates its surroundings. Every muscle cell interprets signals related to energy availability, inflammation, hormonal balance, and mechanical demand before deciding whether to build, maintain, or break down protein. When these signals suggest instability or threat, muscle loss becomes a protective strategy rather than a failure. The body reduces metabolically expensive tissue to conserve energy. From this perspective, forcing exercise or excessive protein into a hostile internal environment is unlikely to yield lasting results. Supporting biology begins with recognizing the body's priorities. As people age, recovery capacity slows, inflammation rises more easily, and metabolic flexibility narrows. The body becomes less tolerant of extremes and more dependent on consistency. When strength training is introduced gradually, paired with adequate rest and nourishment, muscle cells receive a message of safety. Safety is not a psychological concept alone, it is a biochemical state defined by stable blood sugar, sufficient energy, low inflammation, and balanced hormones. In this state, the body allows resources to be allocated toward growth. One of the most overlooked aspects of supporting biology is rest. Muscle growth does not occur during exertion but during recovery. With age, recovery windows lengthen, and insufficient rest quickly turns beneficial stress into damaging strain. When recovery is respected, muscle protein synthesis can proceed without interference from stress hormones that promote breakdown. Supporting biology means allowing adaptation to complete its cycle rather than interrupting it with constant demand. Nutrition functions in the same way. Forcing high protein intake without addressing digestion, inflammation, or insulin sensitivity often leads to disappointment. The body cannot be compelled to use nutrients efficiently if the metabolic environment is unstable. Supporting biology means providing nutrients in forms and patterns the body can actually process. It means stabilizing blood sugar so insulin can act as a growth signal rather than a stress response. It means reducing inflammatory burden so muscle cells feel safe enough to invest in rebuilding. Stress, both physical and psychological, plays a powerful role in this equation. Chronic stress elevates cortisol, a hormone that prioritizes immediate survival over long-term maintenance. Elevated cortisol directly accelerates muscle breakdown and interferes with protein synthesis. Forcing progress under chronic stress is biologically contradictory. Supporting biology involves reducing unnecessary stresses so that anabolic processes can function without constant opposition. Movement itself becomes more effective when it aligns with biological readiness. Gentle resistance, functional movement, and consistent activity send clear mechanical signals to muscle tissue without overwhelming recovery systems. The body interprets these signals as evidence that muscle is needed for daily life, not as an emergency response. Over time, muscle adapts to meet this need, gradually increasing strength in a sustainable manner. Supporting biology also means respecting individual variability. Aging does not follow a uniform script. Genetics, life history, nutrition, and stress exposure all shape how the body responds. Forcing standardized protocols ignores this individuality and often leads to frustration or injury. When the body is supported rather than coerced, it reveals its own adaptive capacity at its own pace. There is a subtle but profound psychological shift that accompanies this approach. When people stop viewing their bodies as obstacles to overcome and begin seeing them as systems to collaborate with, adherence improves naturally. Consistency replaces intensity. Curiosity replaces judgment. These psychological changes reduce stress and reinforce the biological conditions needed for muscle preservation. Time also behaves differently under supportive conditions. Forced approaches often produce rapid but short-lived changes, followed by regression or injury. Supportive approaches produce slower but cumulative adaptations. Muscle fibers strengthen quietly, connective tissue adapts, neural pathways refine coordination. These changes may not announce themselves dramatically, but they endure. The aging body retains an extraordinary capacity for resilience when treated with respect. Studies repeatedly show that older adults can regain strength, balance, and muscle mass when interventions are appropriate to their physiology. This would not be possible if decline were inevitable. It is possible because biology remains responsive, provided it is not overwhelmed. Supporting biology does not mean avoiding challenge. It means delivering challenge in a form the body can integrate. Mechanical load without excessive inflammation. Nutrients without metabolic chaos. Effort balanced by recovery. When these elements align, strength emerges not as a battle won, but as a state restored. In this light, muscle becomes a reflection of internal harmony rather than external domination. Strength returns not because the body is forced to comply, but because it is given reasons to trust that growth is safe again. The body, when supported intelligently, reveals that adaptation is not reserved for youth but remains a lifelong capability rooted in balance, patience, and biological respect.